Namaste and good afternoon, everyone. This is Sanjit Singh, doing PhD in IIT Kanpur, India. My research field is design and development of acoustics metamaterial for sound and noise mitigations. Today, I'm going to discuss about flat fractional spiral acoustics metamaterials, composed of several arms, ventilated metamaterials for simultaneous broadband sound absorption and air circulations. My design is inspired from the Fresnel spiral acoustics lenses. In generally in lenses, people are used Fresnel spiral, and inspired from that, I designed my structure that is allowed to pass through the air as well as sound outflow. So our my outline is that first I will discuss about the need and background of the proposed design. Second one is that uh, what kind of design I am going to show, and the third one is theory behind it and how the material is designed and perform the experiment and results. What the result is came and we will discuss it, and last the conclusion. So we know that nowadays rapid growth of urban population, and because of that there's a lot of noises produces inside the cities, and because of that people are facing a lot of problem in the daily life. If you can see from this graph or this image that New Delhi and Mumbai are the two most world noisiest cities. So we need to, as an Indian, we need to think how we are going to control our urban populations, noise pollutions. So, what? Because of that, there's a lot of health issues happening, um, like noise, headache, exhaustion, insomnia. These kind of problems because of the noise, and because what is the application of this ventilated kind of metal is that now in drones, because drone is an emerging technology nowadays, and in the drones we need to flow the air through this structure as well as the noises in the transverse directions. We can use our structure in a fans and HV systems and residential building where we can use ventilated windows or maybe some shielding over there so that traffic noise, other building noise, traffic noise, and other noises cannot pass through the structure and cannot going inside the room. So in 2020, was researcher proposed this structure, and this thickness is only 44 mm. This is a very complicated structure, and manufacturability is very complicated. The second one is that everything of meter, but in this structure we need to design. If you want to get a broadband sound output, we need to design each pocket, each block of this Librethink structure, so that we can get the broadband sound. If not, we can get a single peak of the sound of the output. In the same case, we in 2020 on one of its the articles were published, and this also show a single peak of sound of the sun, and the ventilated area is 45%. This is also in 2020 proposed by another researcher, but the thickness was very huge, like 12 centimeters, very mathematical. Our structure is composed of two discs, and each disc there is a four channel. You can see from this color that this blue line is shows the one channel, yellow line shows the second channel, pink color is shows third channel, and green you can say that it shows the fourth channel. And these all the channel are in a single plane and placed at 0 degree, 90 degree, 180, and 270 degree. There is another disc back of this disc, and this is rotated by 45 degree, having the same channel length, same thickness, and placed together the back of the first channel, not first disc, and rotated by 45 degree and pasted together. So this is our printed 3D printed samples for the testing, and we can see that only the 20% of the web opening is there. So theory. is like we need to calculate the first the length of the channel, and when once you get the length of the channel from these equations, you can get the impedance of this structure, and then from this formula we can calculate the sound absorption coefficient. This is the proposed panel that we can use as a window, or in a building we can use like this. And this unit cell is composed of the front panel with having a diameter of D, capital D of the this front panel, and the D small d is the opening of this hole that through the air is passing through from these directions, and this one sound get absorbed in transverse directions. This is the experimental setup we performed. Yeah, impedance tube, and this impedance tube is known as PNK type of 4260 impedance tube, in which uh, we calculate the sound absorption in the range of 400 to 1600 hertz. We can see that from there we can place the sample over here, and this is the loudspeaker from which we can generate noise, white noise, and then there are two microphones that can sense the incident and reflected sound wave, and there is a DAC that activates the system. From that, we collect the data and proceed in the computer. We can now this result from the impedance tube that is shown in a blue color. We can see from there, and there is a also performed FEM simulation with the help of ANSYS 2000 ANSYS acoustics module 2021 R1 model. And you can see from this graph that there is differences between experimental and numerical simulations because of the viscothermal losses. We can see that there are four different narrow channel, and because of the narrow channel there is a lot of viscous losses happening in the real time. But when once we do the FM simulation, the FM software not allowed to consider mostly viscous thermal losses in the model. Because of that, there is a differences showing in this graph, but the overall peaks is matching. So we can see that there's a relative bandwidth sound observable. Relative bandwidth sound observable is more than 50%. So we can see from this graph that from 8400 to more than 1600, means more than one active sound get absorbed while performing the ventilations. Now we think about the what happened when we increase the number of turn or number of turn. So when we increase the number of turn, because we need to reduce the width of this channel, because this structure is fixed, dimension is fixed, diameter is fixed because of the experimental constraint, because we need to fix this structure is 100 because it is required in impedance tube. So we designed three samples. Width is 1 mm and height is 6 mm. Number of turn is 3. We reduce the thickness, width thickness 1 mm and 2 mm. Something like number of turn is 4 and number of, so we increase the number of turn also, and reduce the width of this channel. So what we see from this graph is that all the samples are showing the broadband sound absorption, but some other peaks also this is almost showing broadband sound of in all the cases. So that channel width and number of turns does not do not affect much on the sound of person, we can say from this graph. We also perform the ventilation property, where we create a two domain for air domain 1 and air domain 2. From air domain 2, air domain 1, we increase the velocity of flow velocity from this domain, and we also capture the pressure drop from the second air domain. So from the graph, you can see that when we increase the velocity of the sound, velocity of the air, the getting pressure drop increases. And from this formula also we can see that delta P is directly related with the airflow velocity. So that is it. So what is about it? So we propose the thinnest till now reported around 14 mm thinnest material with 90% of sound absorption in the range of 84 to 1600 hertz. It's almost more than one active. sound of the oceans, and the thickness is only 14 mm. Or we consider if we compare with the lambda, means the wavelength of the sound is around lambda by 26. And this consists of that n spiral is total 8 spiral channel in 2 disc. That is one achievement. Thank you so much.